this one is version question 5. My goal today is actually to get 9.1 done, which is what this stuff is, and 9.2. So it's a pretty big goal. So we want to show that this is a solution to that. So basically, we'll start with this fella. And I know I'm going to have to find his derivative and do all this stuff, but I think I should get the derivative first. When you look at a question like this or a function like this, I hope you all see the quotient rule. It's a fraction, so to do it, you're going to have to do the quotient rule. So that's f dash g, take f, take away f of g dashed over g squared. You differentiate the top and you get 1 over x, because that's a number, right? Plus c is like plus 10, so its derivative is 0. Times the untouched g. You leave this guy alone, and you derivative of that. And the whole thing is over x squared. So let's see what we get. That times that gets me 1. You distribute that, you're basically just doing that. And it's going to be over x squared. So I'll come over here and I'll take the left-hand side, which is x squared y dashed plus xy. And that's going to be x squared times this. It's minus. Plus x times this guy. Those cancel out and you're left with that. And those cancel out and you're left with that. And dead. Nice, tidy. It works, right? If you use this in this differential equation, that horrible mess there ends up being 1. That's how you check. Now they have a part B to this question where what they essentially says is pick some values of C and sketch it. Well, I don't have time for that, but here are my values of C. That would be one of my curves. That would be second one of my curves. There would be a third one. Can you see what I've done here is I've made C -1, C0, C2, and you plot them all in your calculator. I think you have to do about 4 or so. And when you put them into your calculator, you get a choice of 4 pictures and you pick the one that looks like it. So can you imagine plotting that in as Y1, Y2, Y3, maybe another one called it Y4, and pick a reasonable window and you're good to go. Are we good with that question? Okay. Next one, not so obvious. Here is a differential equation, which is sometimes called a logistic model. It comes from population growth models. So if you're interested in figuring out how the population of halibut or whatever it is going to change through time, you would use a model, perhaps something like this. So we've got to understand what this is saying. It's saying the rate of change of population with time is 1.3 times the population multiplied by 1, take away the population over 4,800. That's a pretty messy thing. And they're going to ask you questions like this. For what values of P is the population increasing? Well, you might say, well, I can't tell that because I don't know what the formula for P is. All I have is this differential equation. But that's not actually the way you should look at this. The key is in this word here. If the population is increasing, so you imagine this is time and this is the population. If the population is increasing, it would look something like this, right? It's going up. What do you know about the slope of a function is increasing? Well, you know that, right, exactly, it's greater than 0. So all I'm going to do is look at this side and figure out for what values of P is that going to be greater than 0. The first one I'm going to go is going to go this way. Would you agree that you have to have at least some animals or else there's no point to this model? Right, so I'm going to make the assumption that P has to be positive. Can you just mute your background sound there? There we go. Yeah, let's look at this fella here. In particular, here. If P is, if this is going to be positive, right? Doesn't P have to be less than 4,800? Because if P is bigger than 4,800, won't this fraction be bigger than 1? And 1 take away something that's bigger than 1 makes it negative, right? So I'm going to make the assumption. And that can be written down as what? 0 to 4,800, right? Interval notation. When is it decreasing then?
$4,800 to infinity.
Right. And then the third one, because that's like there's an A question, this is like the B question. And then they have the last one, and they use a term I haven't used yet. And what they use, an equilibrium solution. Okay. The equilibrium solution here would be when it's not increasing, it's not decreasing. In other words, the population has reached its natural value, right? The place where things would just settle down and they'd be the same amount of halibut all the time. And that happens at what single number?
4,800.
So do you see that in this model, what you can say is that when the population is less than 4,800, won't it grow, right? You'll get more and more halibut, whatever it is. If it's more than 4,800, the population will decrease, right? The rate is going to be less. There'll be fewer halibut the next year. And when it's 4,800, it's perfect match. And that's called the logistic model. Not that you need to know it for this particular thing, but I'll actually draw it for you. It's quite a cool model. Up here, you have 4,800. And then you start off with whatever it is, and the population grows, and then it levels off. And if you start with the too many, population basically declines, and they meet up here. Quite a cool thing. It's called, if you're interested, it's called the logistic model. It's actually the model that is used for population growth of almost anything. If you want to have a relatively simple population growth model. To remind you, okay, remember 141 and having population growth models that look like that? And I'm sure whoever you got told you that these models are good for the first 3 or 4 years, but they're really bad at predicting 100 years from now, because they basically just get bigger and bigger very quickly. If you did the same thing with this logistic model, the first 3 or 4 or 5 years would look pretty much the same as that. But you see, this one would shoot off and be really unrealistic, whereas this one would level off at, you know, if it was rabbits on an island, the island's only got enough food for 500 rabbits, right? So if you only put a few rabbits on the island, they will grow, right? You'll get more and more rabbits. But there will reach a point where the rabbits and the available food merge, and you can't get any more rabbits, right? If you have too many rabbits, they just eat all the food and they starve and they die, and then, you know, the vegetation gets a break and it grows and so on. So that's called a logistic model. It's a little bit different. Question 7 is just another logistic model, so I'll skip by that one. And question 8, which I'm going to skip over to show you on the screen here. I hope we can, good. We are going to be looking at what might be the graphs to a differential equation, and we're going to decide why it isn't. So this first one, dy by dt is equal to e to the t y minus 1 squared, and they said this is not going to be the graph of that guy. It can't be a solution. And they even go and give you some clues. So let me kind of reiterate the clues. If you look at the value of e to the t, isn't e to the power of t always positive? No matter what number y is, won't y minus 1 squared always be positive? Now you put those two facts together, doesn't that make dy by dt always positive numbers? And that means it has to be always increasing. Can you see this function stops increasing and goes downhill? That's essentially why this cannot be a solution to that. So this function is increasing and decreasing, right? But this fella is greater than or equal to 0, implying that it cannot be decreasing on any interval. So you basically just fill in the missing words to describe what I said there. Okay. This graph here, the second one called B, can't be a solution either. Well, the good news is it's always increasing, so we can't use the argument that we used here. If you look at this equation here, what is going to be the derivative when y is the number 1?
E.
Say that word again?
0.
0, thank you. So does it not mean then it should level off? It should be horizontal. Now, if I look at here, do you see that's perfectly horizontal? So that's good, but that was bad. That's why this didn't work. It's going uphill is good, but at 1, no horizontal. So that's why that one is not a curve, and you fill it in there. And question 9 has 4 differential equations and 4 pictures. And that means I'm going to have to change where we are. Sorry about all this jumping around, but there's a nice piece of software that I have in Canvas that I'm hoping to show you. Right now, you should be looking at our Canvas shell. Agreed? Is that what you're saying? Right. Do you know this guy called GeoBra Direction or Slope Field? That's a piece of software that's going to allow us to, oops, rewind that. That is going to be for our next section. And I will be using that fairly shortly, but it's not going to help you with the question that I'm looking at. So I better not go any further than that right now. Okay. Match these differential equation solutions labeled. So we have a differential equation 1 plus x squared plus y squared. So I'm going to show you that one. And I'm going to tell you why it's one of these pictures, right? Rather than any of the others. Would you agree that 1 plus x squared plus y squared, right, is always greater than or equal to 1? X squared and y squared are positive, right? So the best it can be is bigger than 1. And so I'm looking for somebody that's bigger than 1. Now, as x and y, as x goes to infinity, won't this thing here go to infinity? So I am looking for a graph here that slope is always bigger than or equal to 1. And as x gets bigger, it gets even steeper. And the only picture that suits all those things, that its slope is always 1 or bigger, and as x gets larger, it gets steeper, would be picture number 3. Do you see the logic of why I did that particular one? Now, they're really fun questions, and I forgot about that we can't use that software to help us with. But that's the kind of thing you're going to do. And you have so few examples, I don't want to do anymore. So that gives you it. And we are finished with that section. So I'd like you to say hi while I get set up for the next section. So for attendance, you can say hi. I'm just going to mute again, get some background sound. Wow, you can tell Thanksgiving's coming. We're 8 people missing today. Wait a minute, 1, 2, 3. Yeah, okay. So let's talk a little bit about the next section, then I can use that piece of software I was trying to show you about. There we go. So this is chapter 9.2, and it's called, well, it has different names. This textbook calls it a direction field. And other books, it'll be called a slope field. What it does is it allows us to visualize what a differential equation looks like. So let's take an example. Suppose I had a differential equation, dy by dx, and we'll make it x plus y. Now, I would like to visualize what these derivatives look like at different values of x and y. So can you imagine that you take your normal coordinate system? I'm going to do a very baby version of this. And for every single one of these guys, you put a little dot at key points. Now, the good news, you are not going to do what I'm doing. I'm showing it by hand, and then I'm going to show that cool piece of software and how it does it for us. So for every single one of these coordinate points, we plug its x and y coordinate in, and we will get what the slope would look like at that point. So to give you an example, do you see this guy here? His coordinates are 2, 2. So his slope would be 4. So you draw a little baby line whose slope is 4. Can you imagine rise over run making it 4? Now this guy is 2, 1. So his slope's 3. 2, 0. His slope's 2, 1, 0. Then you got a 3, 2, 1, 0, -1. In this case, you've got 0, so it goes that way. You got a 1, you got a 2, you got a -1, you get a -2. Oh, here you've got a slope of 1, 0, -1, -2, -3. It wasn't particularly accurate. But do you get the gist that every single point you draw a little line of the slope that is equal to? And this is called a direction field. Now, what it is it's visually representing this differential equation. Now, if someone then says, I know that the solution, right, the particular solution to this differential equation, excuse me, passes through the point 1, 0. You can actually use this to try and predict what the curve, what the y would look like. So I know it's here. It's pointing that way, and then it gets to here and it points that way. So can you imagine it would go like that? Now it's going to point this way, it's going to hit this guy, and then it's going to curve up like that. Do you see that that gives me an idea that this particular one might look something like that? Now, if you told me that it passes through here, which is what, 0, 1, imagine it's going here, it's going to go here, it's going to go up, it's going to go here, it's going to go flatline. I don't have enough guys, but I'm assuming it goes up, and that would be a different one. Now, wouldn't it be nice if there was a piece of software that allowed us to sketch these guys and to do things like, if I tell you a boundary condition, to draw the curve that would pass through that particular direction field. One of the ways to look at the direction field, forget these little rhymes for a minute, is, can you imagine you were trying to model the current on a river? And you imagine you dropped a little boat here. This would be the kind of pathway that the boat would follow, right? So it's actually quite a complicated situation here. It's modeling lots of things at the same time. So now I'm going to go and show you that nice piece of software. I can find where the heck I put it. Is it here? Is it here? Here we go. Just getting into our class. There we are. I don't know. Are you looking at the slope field thing? Okay, good. So the way this thing works is you basically put the equation. Now, do you see this as f dash? That's my dy by dx. And you see the x plus y. And you see that at each point, they've got little lines that are the slope. Yeah, see that guy there? You see that little line is horizontal? Maybe if I make it a little bit bigger for those who, there. You see it's horizontal there, exactly as it should be. Now, suppose I know that it passes through the point 2, 0. If you put your mouse pointer on it, you can drag it to here. Do you see what the curve would look like? Imagine that's the path that something would take if you dropped it in the water. Right. Suppose we took the solution, we took it up here, or we move it. Oh, there's a change in direction. You see when you go there, it totally changes. Now you can put any function you like in here. How about this one? X squared plus y squared. I think I have to click out of it to let it reset. There you go. And do you see that direction feels quite different looking? And if I don't like the values of x, you can change this to -2 and 2. And click out. And then I think I just do a little zoom in. Come on, zoom in. There we go. Now I can move this thing. I should be able to move it. No. Evidently you can't move in when it's in zoom mode. Right. Well, it kind of worked. Are we back to this hill again? Right, there's a fill. So, to give you an example of what you're going to do, a lot of these questions in this section are, here is a derivative, right, a differential equation. And here are some pictures. Which one does this guy belong to? So, if I said to you that the derivative was 16, now I'm not sure how to do pi in this thing. I think you go pi. I think you go pi. That might work. Cosine of bracket. Not sure if I can get pi in, but I'm going to try. I'll do it that way first. If it, oops, didn't like that. Okay, then plan B. Let's make it 16 cosine a 3.14 y. Okay, I'm having distinct issues with this piece of software. It works quite well without the cosines, but right now I've buggered the darn thing up because I think I'm on that mode. You know, this worked perfectly well this morning. Stop laughing, that's cruel. It worked really well this morning, and then everything's went wonky. Okay, out of this guy, back into my class. That should reset it. Okay, that looks okay. Let me try and change this in small ways. Hey, now it works. Go figure. So you type in your guy and you find out which one he looks like, and then you can play about with them. I'm going to see if I can do another example. This is question 2, for instance, where the derivative is 8 take away y. I may have to put spaces in. Not perfect. The next one after that is x brackets 10 minus y. There you go. So this is what the direction field or slope field would look like. And you have a whole load of guys that, if I click this here to make that go away, you have a whole load of choices to see which one this guy looks like. So that's pretty much what happens there. Let me see if I can find something a little bit interesting. Let's try this one. This is question 6. Like, you're going to have fun playing about with this as well.
Professor.
Yes.
So the curve that shows up, that's the curve of
a particular solution.
Is that the function that, like, not the derivative function?
Correct. The green thing is the function. So in this one here, do you see as I move this thing around? It's quite an interesting one. Do you see as I move this around, this green line represents one solution to that differential equation that passes through whatever the coordinates of that point is. Now, if I click on a few more of them, what you get to see is a whole family of those functions. So if I, for instance, move these guys the way I did, there we go. There we are. Can you see this is a really weird differential equation? Doesn't it look like if you pick a point up here, doesn't it flatline straight onto the x-axis really quickly? Just kind of weird. I'm not quite sure what that represents, but it's just a function. I guess it represents whatever it wants to. And then if I choose values that happen to be, say, below the axis, you see that the difference is that they curve up, but they still work along that line. If you look right along this line here, don't you have the value that the derivative when y is 0 is 0, and that explains exactly why that does that. Eventually, if this function becomes 0, won't the derivative be 0, and they'll just flatline along the x-axis? So that's why that one's doing that. Right, this is y minus 2x. So y minus 2x, boom, there's your guys. Okay, I'm interested in these curves. Let's take out these solutions for a minute. And we are told in question 7 that it passes through the point 1, 0. So I'm going to grab this guy and I'm going to put it as close to 1, 0 as I can get. Now, do you see that visual picture? I'll scroll it down a bit. That's the direction field, and this is one particular solution. So how does that work in your homework? Because I haven't even shown you your homework yet. Your homework's really quick. That's not the picture I wanted to tell you. Let's try that again. Where is screen 2? Here we go. Can you see the, shrink it down a little bit? Right. Up here is the equation I typed in. If you can remember the guy that we just drew a little while ago, wasn't he that fella? So what you'll do is you'll take this piece of software and you will type that fella in, right? The y minus 2x part. You'll click on solution and you'll move the little dot to 1, 0. It will draw in green the curve and it will look like one of these 4 pictures and you will pick the right picture. So here's another guy, right? See this one here? I'll write it down. Y dashed is 3y plus 9xy. And it's passing through the point 0, 1. So I'm now going to go back to our piece of software and try that guy out. See here? So I'll go, oops. I'll go up to the top and I'll change this fella into 3y plus 9xy. Right, so that's the differential equation set up. Let's change the size of this. There we go. If I click on this now, I get a solution. And we want it to pass through the point 0, 1, which is here. Do you see basically a big happy face? Right. So if I zoom in on this a little bit and maybe move it up a little bit, you got that. Now keep that guy in your brain. Let's see. Which one of those 4 guys was the closest to the green one that I had a few moments ago? Numbers top left, right, bottom left, right. Which one was it?
Bottom left.
It was. It was a big happy face, but it was on this side. Oh. So do you see you're just going to basically pick a picture for the most part? Now, in the later groups of questions, it gets a little bit trickier. And so here's question 9, because you won't be able to use the software because they do not give me the equation. All they do is they give me, right, the direction field. But they tell me it passes through the point y0 is -2. Do you know that's another way of saying when x is 0, y is -2. So they've just told me it's there, right? Now, if you imagine there, can you imagine leaving on this side, it would go like that? And then if you left it on this side, you see it's going like that. So the answer I'm looking for is a hill that peaks at 0, 2. And that makes it this one. And it's a very visual thing I've done there, so maybe I should try it again. That point there has to be used, right? It has to be at 0, 2. If you move a little bit to the left, you see
-2.
Oh, thank you. 0, -2,
Yeah.
right? So as you move to the right of 0, -2, do you see that the slope field, think of it like a current, right? And I dropped a little boat there. The little boat would travel something like this, wouldn't it? And then if you went this way, the little boat would travel like that. And the shape that matched that one
Would be option 4, bottom right.
Yeah, that one.
Because it's -2?
Yeah.
Yeah, okay.
Because it's -2. Right, now if you did 0, -1, yikes, you'd start here and you'd get basically just a bigger version of what I just did. And it would be that one. Are we good with this? Because I have to jump up and down, but you can imagine having it and just, on the screen, touch your finger if you like, and just follow the path. You're still picking pictures, you're not doing too much. Right, here's another example of that same one. Here's a direction field that looks like this. Suppose I tell you it's 0, 8, which is about here. Right, if you were here, wouldn't you curve up the way on this side and then this way? So it looked like a happy face, kind of straight line on the left, happy face passing through 8, happy face passing through 8. Looks like that one, kind of straight line on the left. We good? Right. This guy here, I suggest strongly that you go back to the software and you type it in. And then couldn't you just put this fella in, 0, 1, and see what it looks like? 0, -1, 0, -3, and 0, 3. And when you put it in, you should have some pictures, and it'll be one of those guys. Okay. Now, find all the equilibrium solutions. All right, let's return back to here. An equilibrium solution are values where the function will have 0 derivative, okay? In this case. There are 3 different values of y that make this differential equation 0. There are 3. So let's go hunting for them. Tell me the first one.
0.
Would you agree? The minute you make that 0, won't the whole thing be 0? Right. There are 2 more, and you're going to get them out of here. The 1
2 and
minus
-2.
Right, so 0, 2, and -2. 0, 2, and -2. Here's another one of those direction fields. If you can figure out how to make the software do it, great, but couldn't you just use the picture and just draw 4 guys and one of these 4? You know, they remind me of Mick Jagger's lips. Don't know why that came into my head, but I had to share it with you. That's what that picture looks like to me. Here's another guy. Pick 3 solutions and see which one it is. Right, this one says 9 plus 9y. I think I'll do that one. So that's going to be our last one for today. So I've just typed into that piece of software the differential equation. You're looking at GeoBra right now? Yeah?
No.
Okay. No? Let me try again. Got so many windows open now, I'm not sure where I'm pointing. You're looking at it now?
Yes.
Okay. So we have 9 plus 9y. That's good. I'll put in some points. I'm going to zoom back a bit. Okay. They're kind of random points, so interesting. Just looking at my choices here. Maybe bring this one just randomly here. Okay, that'll do. Do you notice that the ones up here flatline here, and the ones that you pick down here flatline here? They all look like they're flatlining on this value, y equals -1. So keep that picture in your mind for a few seconds. One of these 4 was like the one that I just drew. Agreed? Now, didn't it flatline at y equals -1? So it can't be these two. So it's this one or this one. Did it curve down like this and curve up like that, or did it do the opposite? Can you remember which it was? Top one?
right.
Yeah, it's that one. Now, they don't have to be a perfect match because it's all to do with scale, isn't it? You know, if I increase the x or y values, things would get fatter or taller, and you might not notice it. So don't look for perfect fit, look for pattern and shape. Right? And that's got the right pattern and shape, right? And I think we are finished for today.